Hi, Assalamualaikum. My name is Muhammad Nakiuddin bin Senin.
I am Ami Aziz bin Wahid Ghaffar from 2 VMMV, Section 1.
Hello, my name is Faris Farhan bin Murni from 2BMMV 1/1.
Hai, Assalamualaikum. My name is Muhammad Abi Alwi bin Muhammad Ali.
Assalamualaikum, my name is Muhammad Amirul. So today we are going to make our video meeting for our heat transfer assignment. Okay, for the abstract, the research present the result of numerical study of heat transfer and pressure drop in a TEG that is designed with different shaping fins. The TEG used for this research consists of a rectangular duct fitted with different shaping fins and is heated from the lower plate. The pin shape and the compact TEG configuration were numerically studied to maximize the heat transfer and minimize the pressure drop across the TEG. A three-dimensional finity volume-based numerical model using SolidWorks was used to analyze the heat transfer characteristic of various pin fins. The simulation applied to estimate the heat transfer coefficient and pressure drop for a wide range of Reynolds number with different pins.
Okay, I will present about introduction for this assignment. Okay, heat sinks are used in electronic device and assemblies to provide supplemental cooling that is required to prevent overheating of component. These elements are designed and optimized to ensure the electronic device operate within the temperature range provided by manufacturers. Heat sinks are designed using thermal-conductive material like copper and aluminium, and they work by dissipating heat through liquid cooling, natural convection, forced convection, and radiation. Thermal management needs vary from one application to another. Therefore, it is essential to look beyond the heat sink when designing a thermal solution for a particular application. Some of the important factors that should be considered include heat sink level requirement, component level requirement, system level requirement, and chassis level requirement. Okay, next, the heat sink transfers the thermal energy generated by an electronic assembly or component into a cooling medium. The heat is transferred from a higher temperature region to a lower temperature region by conduction, convection, radiation, or by a combination of these heat transfer methods. The performance of this specific exchanger is determined by many factors, including the velocity of the coolant fluid, the thermal conductivity of the material, the thermal interface material, and the attachment method. For a specific application, the parameter of a heat sink can be precisely determined through modeling and analysis. Okay, thank you.
Okay, Assalamualaikum. For the theory of this project, firstly, heat sink transfer thermal energy from a higher temperature device to the lower temperature fluid medium. The fluid medium is frequently air but can also be water, refrigerant, or oil. If the fluid medium is water, the heat sink is frequently called a cold plate. In thermodynamics, a heat transfer is heat reservoir that can absorb an arbitrary amount of speed without significantly changing temperature. Practical heat sink for electronic device must have a temperature higher than the surrounding to transfer heat convection, radiation, and conduction. The power supply of electronic is 100% efficient, so extra heat can produce may be detrimental to the function of the device, as much a heat sink is included in the design to disperse heat. So next, to understand the principle of heat sink, consider for Fourier law of heat conduction. Fourier law of heat conduction is simplified to one-dimensional from the x direction. Show that when where its temperature gradient is in body, heat will transfer from the higher temperature region to the lower temperature region. The rate at which heat transfer conduction is proportional to the product temperature gradient and cross-sectional area through which heat is transferred. So the formula for the Fourier law is Q K equal to negative K A d delta dt per dx. So for the heat, for the thermal heat in heat transfer, there are a few factor for the theory, which is thermal resistance, material, fin efficiency, and fin arrangement.
Okay, Assalamualaikum. So I will present about methodology. Okay, first of all, the assuming for this project, we assume ambient temperature used 301.15 Kelvin, convection coefficient used 5.03, and heat power assumed 10 watt. Okay, we use SolidWorks simulation to get the thermal or temperature, minimum temperature and maximum temperature about this project. Okay, first we can see base that we create sizing 120 times 60 times 40 mm. Okay, the minimum temperature for simulation base we can get 120.32 degrees Celsius, and maximum we can get 131.84 degrees Celsius. Okay, we go to the design 1. Design 1, that is the normal size for the fin. Only fin we use 40 mm, the higher of fin, and gap 1.5 mm, and number of fin we have 132 fin. With minimum temperature we get after simulation, we can get 33.92 Celsius and 34.30 degrees Celsius. Sorry. Okay, for design 2, we redesign this fin, but we make different height and gap between fin. Okay, for the design 2, the height is 60 millimeters and gap between fin is around 2.0 mm, and number of fin 100 of fins. Okay, you can see we can get 32.5 degrees Celsius and maximum 32.86 degrees Celsius. Okay, that's only fin. After that, we combine the base and the fin using assembly SolidWorks to get more minimum temperature that maybe we can get. Okay, for the base and design 1, we can get minimum 33.23 degrees Celsius and maximum 33.58 degrees Celsius. Yes, closest. For base and design 2, minimum degrees Celsius, we can get 31.89, sorry, and maximum 32.12 degrees Celsius. Okay, for the model information, you can see design 1 as below. Solid body, volumetric parameter, document pad modified. You can get mass, volume, density, weight from here. Information for design 2 like this, same as design 1, because we just change the height and different gap. Okay, for the properties of design when you use cast stainless steel. For the base, we use cast stainless steel, and for the fin we use aluminium alloy. For design 2, same as design 1. Result thermal, you can see design 1 we get minimum 33.23 Celsius, maximum 33.58 degrees Celsius for design 1, and for design 2 we can get 31.89 degrees Celsius and 32.12 degrees Celsius. Thank you.
Okay, discussion. As you can see on the graph, based on the graph, it's shown that the minimum temperature on cold side of the heat sink for design 2 is better than design 1. As the simulation conducted, the heat power is remain constant for the two design, which is 10 watt, and the material of the heat sink are 1060 alloy. But actually, both design have the same material and fin type of heat sink, but they got different between length of fin, gap between fins, and number of fins. As we can see in table 1, the length of fins and the number of fins in design 2 is more than design 1. That's why design 2, the minimum temperature for design 2 we got 31.89 degrees Celsius, while design 2 we achieve 33.23 degrees Celsius. Okay, as you can see in table 2, this table is about thermal conductivity of material. As you can see, the copper metal have highest thermal conductivity. So actually our simulation do not achieve the target of temperature on the cold side. This is because we need change the material of the our heat sink into copper material. Based on the table that we can see, copper is good material to design the heat sinks because thermal conductivity of copper is higher. That's why it can transfer a large amount of heat. Then if you want to increase the rate of heat transfer, we need to increase the surface area of that attached to the surface of fin. Maybe our design will get temperature within 30 degrees Celsius. Okay. Actually, lastly, the best suggestion of heat sink is actually by using copper, but aluminium is the most common material for heat sink. It was to why always use aluminium, because aluminium fit the needs of most project around the world, and this metal is lightweight and has relatively good thermal conductivity.
Bismillahirrahmanirrahim. Okay, Assalamualaikum. Next, we turn to conclusion. For the last part conclusion, I can say this study shows that the quality could be improved by changing some of the operating parameter. However, to obtain the best quality, some recommendations should be followed. Moreover, in each case, the fluctuation in the operating parameters should be kept as low as possible. For the best quality in all, heat sink optimization helps us to determine the dimension, weight, and thermal performance in order to meet design requirements. As shown, finding the optimal number of fins determines the best solution for temperature at the base of the sink. The goal is to determine the optimal number of fins in order to maximize heat transfer. Thickness for the fin is the major parameter to heat sink performance. Although thinner fin increase the optimal number of the fin, they actually decrease their weight of the heat sink and improve the heat sink thermal performance. There are still some issues remaining to be done. The next step for the quality and the productivity improvement are decrease the reject production. It will increase both the productivity and the quality, increase the productivity rate for the present setup and fluctuation in the content of the alloying element. For conclusion, although all assumptions uniformly temperature at the base and the fin, brace, fin and heated made in the model formulation are not satisfied perfectly. There are more than satisfactory for the most engineering calculation. That's all from me. Conclusion is dapat. Thank you. Assalamualaikum.